Hello friends, welcome to the lecture on the statistics for hypothesis testing as a part of the course on introduction to statistical hypothesis testing. Before I list the objectives of this lecture, it will be a good idea to recap what we have learnt in the previous lectures. Now, if you recall, we had a general procedure for hypothesis testing that we went over in the motivation lecture, and let me make use of the board to explain what we have done and now where we are heading. So, what we have said in hypothesis testing, that is as a general procedure, we said we will first identify the parameter theta that we want to conduct our hypothesis test on. So, this is the parameter of interest. So, what does this theta denote? Where does it all come from? Well, we said there is a random phenomena which is characterized by a PDF, and we said we use the term population to denote all possible outcomes of this random experiment or random phenomenon, and this population is characterized by this random variable x. Let us say this could be our solid propellant burning rate, or maybe the diameter of a nylon connector, or anything else as well. Associated with this random variable, we have either a PDF if x is continuous valued, or a PMF, probability mass function, if x is discrete valued. Now, this PDF here is typically characterized by certain parameters theta. If it is a Gaussian distribution, for example, this theta would be mu and sigma square. So, for a Gaussian, the parameters of PDF are mu and sigma square, that is mean and variance. If it is uniform distribution, then theta are the range, theta is a vector of the range of values of the distribution, and then if it is a binomial random variable, then you have the p, theta is actually the p, the probability of success, and so on. So, every PDF that characterizes a random process or a random phenomenon is characterized by these parameters, and in basic statistical analysis these are the parameters of interest, that is the parameters of the PDF. In a more advanced analysis such as in maybe linear regression or in time series modeling, this theta would include more than just the parameters of the PDF. For example, theta could include model parameters such as the slope or the intercept and so on. We will however restrict ourselves to these kinds of analysis to begin with. When we go to linear regression, we will include more more elements into this theta. Now, this is the first step in hypothesis testing, if you recall, identify the parameter of interest. And let us take an example to understand what we are trying to do here. Let us take the solid propellant burning rate example number 2 in the motivation lecture, where we were interested in testing whether the average propellant burning rate is 50 centimeters per second. So, we are interested, for example, in mu. So, the theta then is simply mu. What about sigma square? When we are testing hypothesis of this forms, we may assume that the variance is known or unknown. We will even simplify the problem, assume that the variability is known. Now, in order to conduct such a hypothesis test, what I have to do is, of course, ideally what I would like to do is look at the entire population and use the definition of mu, which is that it is an expected value of x, that is it is the average value of all possible burning rates, that is I look at all possible specimens coming from the manufacturing process and then experimentally determine the burning rate, take the average. Clearly, that is an impossible task to finish in finite time. Therefore, what we do is we collect a few specimens randomly, and then constitute what is known as a sample. That is the basic idea. So, we are moving from the ensemble or the population space or the outcome space to the sample space, where the sample consists of a subset of this, and what kind of subset? A random subset. That randomness is very important, so that we do not introduce any bias in our eventual decision that we will take based on the sample. We have spent quite a bit of time in the last few lectures understanding what is the theta, how are the theta defined, what is the interpretation, what is the PDF, what is the probability mass function and so on. So, mostly we have learned the theory, although it is a bit boring, but it is a necessary boredom you can say, so that when we move to the sample space, this is the practicality, this is theory. Here we have let us say n observations of the same random variable denoted by the subscript. So, the subscript here denotes the specimen number, x is the same random variable of interest to me. In the solid propellant burning rate, x is the propellant burning rate. Now, my goal in statistical data analysis as far as hypothesis testing is concerned is to take these n observations and then draw inferences of this mu which I do not know through this sample mean that we work with so frequently, right. The big x's are the random variables, the small x's are the values that these random variables take. The burning rate that comes out of each specimen is actually is a random variable, and I am adding up n such random variables to obtain x bar. Why am I doing this? So that because I believe that this x bar is an estimate of the truth, which I do not know, and hypothesis testing is about making some comments, verifying certain or testing some truth statements about mu based on the estimate which is x bar, this is called the sample mean. In general, statistical inferencing is about drawing inferences about the population from the observations. For this specific example of hypothesis testing of mean, we may work with this estimate or some other estimate. This need not be the only estimate for mu. There are other ways of estimating mu. For example, I can use sample median, sample mode and so on, but the truth is one, that is what should be remembered. So, the entire idea now is we are moving from the population space where we have learned the theory that helps us understand this statistical description of this population or a probabilistic description of this population, to sample space where we are going to work with what are known as statistics. So, we are moving from probability world to statistical world. And what is a statistic? In general, any function of the random sample that I collect is a statistic. That means a random sample that I collect, here is not specimen, the random sample consists of burning rates of those specimens. Whenever I subject it to a mathematical operation and produce a new number, then that new number becomes a statistic. Of course, we have to choose statistics based on what we are trying to estimate. And the important thing that should be remembered is, since each xi is a random variable, x bar also inherits the DNA and therefore is a random variable. So, this is the main thing. So, now in hypothesis testing, what we are going to do is use x bar as a means of testing some claim like this, where the null hypothesis is mu equals something, mu naught, and the alternate hypothesis for example could be it is not. It is a two-sided test, for example. In the solid propellant burning rate example, mu naught was 50 centimeters per second, and of course, in the alternate hypothesis as well. So, from probability to statistics for the purpose of hypothesis testing, what we will learn in this lecture is we are going to learn briefly about how to sample, very briefly, but mostly about what is a statistic, how do I analyze this statistic, because this is a random variable. This is also, it also has its own PDF. That is a very important point to remember. The moment you say something is a random variable, it will have its own PDF and rightfully it has its own mean and it has its own statistics and so on, variance and so on. So, like any other random variable, it has its own PDF, it has its own mean, it has its own variance and maybe other moments. What statistical analysis will tell us is, given some information about where this x's came from, that is some idea of the population, not necessarily fully obviously. If I know fully, then I do not have to sample, I know everything about the population. Given partial or no information about the population, firstly, how do I construct this PDF, and then what can I say about mu and sigma square, that is point number 1. And point number 2, very importantly for the course, which is hypothesis testing, how do I now use this x bar and this information to carry out the hypothesis test. So, I am using x bar as a means or as a vehicle for carrying out this test, and we will see through, I will show you through a simple illustration in R as to why this piece of information is very important for conducting the hypothesis test. That is the crux of at the crux of hypothesis testing. Simply constructing an estimate will not allow us to conduct a hypothesis test. We have to go further and construct the PDF somehow, either through theory, there is a theory for that, and then or through simulations, what we known as what we call as Monte Carlo simulations. That is more of an advanced stuff. We will mostly work with cases where I can theoretically construct PDF of x bar, and then from this I can actually carry out the hypothesis test. At this moment, for beginners it may not be so obvious as to how the PDF of this estimate is responsible or is going to help us in carrying out this hypothesis test. And one more piece of information that I want to give you is, we will generally use theta as the parameter and theta hat as its estimate or as a statistic. This usage of hat in estimation theory or in statistical analysis is quite common to denote that it is only an estimate and different from truth. Theta is the parameter and theta hat is the estimate, and theta naught is the truth. Which I do not know. So, I do not know the truth and I am going to make some conclusions, draw some conclusions about this based on the estimate, but before I do that I will have to construct the distribution of the estimate. This is what we call as the sampling distribution. So, hopefully now it gives you a feel of where we were and where we are going to go in this and the next lecture. Once we have understood all of this and a simple example of how to use this to conduct a hypothesis test, then the procedure fortunately is the same for all parameters. That is very nice of this hypothesis testing, that it has the same procedure for all parameters, and that is why we outlined a general procedure. Therefore, what we shall do is, initially we will go through a simple example, maybe a few minutes into the lecture, which will give us an idea of why this is important in hypothesis testing. What is this? This is called a sampling distribution. This f of x bar is called a sampling distribution, or also called the distribution of the estimate, either way, but we will use the term sampling distribution. First, an illustrative example where we will just argue intuitively and use some common sense to understand what is the role in hypothesis testing, and then gradually realize maybe a couple of lectures later how exactly we use this in hypothesis testing. Okay. So, with this with that prelude, let me list the objectives. We will learn briefly about sampling and estimation. I will take this opportunity to briefly talk about estimation, because as you have seen in the blackboard discussion that what is at the core or crux of hypothesis testing is estimation. Only when we estimate we can proceed towards hypothesis testing, or even for that matter any other data analysis exercise. Once we discuss those, then we will spend some time on statistics and also spend a lot of time on sampling distribution concepts. In this lecture we will only talk of distribution of sample mean, exactly what I have discussed on the board, and in the subsequent lectures we will look at distribution of sample variance, sample proportion, sample and sample correlation. So, I have already explained this as to why we are moving from probability to statistics because of practical reasons. There is no way I have access to the entire population. If I have that, then there is nothing to worry about, in the sense I just get the truth straight away. It is that difficulty that I have which is forcing me to look at sample, a random subset. So, the main point is we have only finite observations of phenomena, and from these finite observations can we say something about the population? That is the main question of interest. So, as I said earlier, what we are doing is we are moving from probability to statistics, where we are moving from the ensemble space to the observation space, you can say so. And in the course of this statistical analysis, that is analysis of observations and the uncertainties arising as a consequence of the uncertainties in the data, that is what all that constitutes statistical analysis. We have two important questions to ask. What kind of analysis is necessary? Obviously, that depends on the purpose of statistical data analysis. In this course, the purpose is hypothesis testing. In some other exercise, it may be regression. In another exercise, it may be classification and so on. So, what kind of analysis is necessary depends on the application. And then what kind of data do we actually require? How do we collect data? Are there some guidelines? Are there some rules that I have to follow? Is there a theory to it? Yes, there is a lot of theory to data acquisition in statistical data analysis, which is put together under the banner of sampling. Pretty much like in signal processing what you have as sampling, but here it is not about, in signal processing it is all about thinking of what sampling rates should be chosen and so on. Here it is not about necessarily sampling rate, it is about how I collect the sample, mainly within a sample whether the observations should be independent or should be can be dependent, then what is the consequence, and all such questions are addressed. And also very importantly, when I collect observations, they should have sufficient information about the parameter of interest clearly. So, suppose I am looking at let us say I want to know what is the average temperature outside this room, and I am going to look at let us say the heights of the population here in this city, and from there I want to infer the average temperature outside. Clearly there would not be much information about, or no information about, the average temperature from the height readings of individuals in that city, correct. Then we say that the data is not informative at all. Now, if you turn to the world of statistical data analysis, there is a quantity known as Fisher's information introduced by Fisher, which is quite wonderful. It characterizes the amount of information that is present in the data with respect to a certain parameter theta. We are not going to talk about that at all. In a full fledged let us say time series analysis or statistical data analysis course, we will have many opportunities to do so. So, the bottom line is statistical analysis not only helps us in analyzing data, that is giving us methods to analyze data, but also tells us how we should collect data and whether the data is informative and so on. Clearly, because the quality of analysis depends on the data. So, any analyst should be clearly worried about the quality and the information content in the data. Many a times we may not have control over how the data was generated, but knowing the impact of uncertainty in the data on the final analysis is always helpful, because let us say you have a data which is of poor quality or not informative and so on, you can straight away say that either upfront, that you can say that, well, the inferences that I am going to draw are going to be highly unreliable, and then whoever supplies the data may have to work again, repeat the experiment to produce better quality data. In this course, of course, we are not going to worry about any of that. Very briefly we will talk about sampling, but mostly focus on the analysis again in the context of hypothesis testing only. So, there are three central concepts, as you have listened to me speaking during the prelude to this lecture, which is that of population, which is a collection of all possibilities of a random experiment, and then statistic, which or the samples, which actually is a subset of the population that I am observing. Many a times in time series analysis, this single sample is called a realization, because we use one sensor to collect a small n number of observations, and what we have is not the truth, but the truth as perceived by the sensor or as realized by the sensor. Imagine that many of us, there are many who watch a movie in a movie theater. Imagine that situation where the movie that is being screened is only one, truth is only one, but each person in the audience perceives a particular scene, entire movie in a different way. So, if you were to ask the opinions or the review ratings, they would vary widely perhaps across the audience. No two movie watchers may give you exactly the same review. So, what is happening is that the truth is one, but what the person is reporting is his or her perception. So, sensor is actually watching some phenomenon, observing some phenomenon, sensing some phenomenon, and giving you the truth plus its own characteristic which has the randomness in it. And that is why a different sensor can give you a different reading. So, we are actually working with what is known as one data record or one realization. This term realization is mostly used in signal analysis, not so much in statistical data analysis. And then we have inference. Of course, this is the concept that we have been speaking about, drawing conclusions about the population based on the observed data. And what we have is a finite data set, and we have to live with that. That is the point. So, the main point to remember is, since I have not seen the entire population and I am only going to see a finite subset of the population, whatever inferences I draw from this finite set will always be in error. So, for example, in the earlier discussion on the blackboard, the sample mean that I am using to estimate mean will never be identical to the truth. As long as the number of observations is finite, no way you can get actually the truth, unless the observations that you have obtained is the entire population itself, which is not necessarily the case for us. So, that is a point to remember. X bar is always going to be different from mu, or theta hat is always going to be different from theta naught. And apart from the three concepts, we have three entities in statistical data analysis. One is the random variable, that is an entity which is the main object of interest, main variable of interest, based on which I am actually formulating the entire problem. In the solid propellant burning rate, the burning rate is a random variable, or in the proportion of defective items in a manufacturing process, the state of the part that I am analyzing, whether it is defective or non-defective, that is a random variable, and so on. So, that is the number one entity that is going to participate in the statistical data analysis, and then of course is your observation set from which you are going to draw conclusions about the ensemble. So, there is a truth which I know partially or I do not know. There is a random variable which I know exactly what it stands for, and then there is a data which I have collected. These are the three ingredients that participate in the statistical data analysis. And there is an implicit assumption, whether we state it or not, I am sure it is common sense, that when we collect this finite observation set, we assume that it is representative of the process. Now, all of this that I am saying is not just valid for hypothesis testing, it is also valid for in general statistical inferencing. Slowly we will boil down, we will drive ourselves towards hypothesis testing, but these are the generic concepts that have to be learnt regardless. Now, this is an important assumption that the finite observation set is representative of the true population. As an example, suppose I want to find out what is the most visited park, okay, or I want to know what is the if I take a particular park, I want to know what is the average number of people visiting this particular park in a day, right. Obviously, the number of people visiting a particular park will vary across days and it is quite unpredictable. So, I can think of the number of people visiting a particular park as a random variable, and I am interested in knowing what is the average number of people visiting that particular park. Now, I will not have access to the entire population, therefore, I will have to randomly sample some individuals who come to this park and somehow carry out my experiment to figure out the average number of people, right. Now, if I am doing my experiment properly, I will actually select the proper set of individuals, but if I am not so careful about the experiment, I may end up actually selecting people only who come daily to the park, and as a result, if all the individuals in my sample are people who come daily only somehow because by virtue of sampling, then I may end up with a wrong answer. On the other hand, I should just randomly sample the number of the individuals who come to the park and ask them how many times they have gone in a month, and that will probably constitute a better sample. So, that is what we mean by proper or a careful sampling, and also mean that the finite observation truly represents the population. So, I should not confine myself systematically or knowingly towards a subset of the population, it should just be randomly done, and that is what is the idea of random sampling. And now, let us say once we carry out this sampling, so let me actually quickly talk about sampling and then come back to move on to analysis. So, sampling is this act of obtaining a subset of data from a population, and a random sample is that which is obtained in such a way that there is no systematic or known bias in your observations. The other way of saying that is all the observations are independent of each other, which means a joint PDF of the observations is going to be a product of the marginal PDF of each observation. Now, let us talk about statistical analysis. So, I have now samples with me, and now I want to proceed towards analysis. As I said, I am just taking this opportunity to talk about some general things about statistical analysis, and then very quickly we will move on to inferential analysis for hypothesis testing. Typically, the first step in data analysis, even in hypothesis test you should be doing this in fact, is to visualize the data, spend some time with the data, do not simply take the data and load it into some software package and then report the outcome. Then you are not really, the user is not needed. I can write programs that will automate all of this. The user's role is in interpreting the results in the context of the process from which the data is being obtained, and also corroborate the results qualitatively with a visual analysis, and see if everything is meaningful and so on. So, there is still quite a bit of user intervention that is required, and the first intervention that is required is graphical analysis, where we first look at the data in the form of displays such as scatter plots, box plots or pie charts and so on. So, there are a number of ways in which you can graphically represent the data, and the kind of display that you would choose obviously depends on the data and the application, but standard plots include scatter plots or bar plots or box plots, where they tell you immediately, they tell you what is the range, or what is, if there is a trend, or if there is an oscillatory component, or if there is an outlier, where is the center located and so on. So, there is a lot of analysis that we can make through a visual inspection, and we should never undermine the role of that visual inspection. Once we have done that, then we can move on to numbers. As an example of the importance or the power of the human brain in visual analysis, let me give you a simple example where we are looking at an oscillatory wave in the context of pattern recognition. If I am looking at a sine wave, then with a human eye, let us say there is only a single frequency, instantly we recognize that there is an oscillatory behavior, and a bit more careful analysis will also help us reveal the frequency of the oscillation. Now, to do this mathematically and with the help of a computer, one has to convert the signal into a Fourier transform, into the Fourier domain through the help of a Fourier transform, compute the spectrum, search for the peak, and then locate the frequency at which this peak occurs. So, there is so much of processing that is required. We do not know at the moment how our brains are able to detect so easily. Of course, our visual inspections has their own its own limitations, but there is a lot of information, qualitative information and sometimes quantitative, that we can gather through visual examination of the data, which is otherwise quite difficult through a mathematical or a statistical analysis. Once we are through with identifying all the outliers, making amendments for the data and so on, then we generate numbers which will tell us more about the data, what we could not gather visually. What we mean by numbers is computing mean, computing median, mode and so on. Those are the preliminary kinds of steps that we normally take, and you should also do that in hypothesis testing. It is not that simply I take the number, generate the estimate or the statistic, then generate the PDF, the distribution, and then apply it, plug it into the hypothesis testing procedure. That is not how we do it. Once we are done with that, then we move on to drawing conclusions, where we move into the world of inferential statistics. This is where now I am going to estimate certain parameters and draw some conclusions about the population, either the population or the population parameters. And in particular, we are interested in hypothesis testing, which is concerned with validating some postulates about the population based on the estimates that I have obtained. And again, associated with this statistical analysis, as we know, is a random sample, there is a statistic. So, what do I need for statistical analysis? I need a sample, that is an observation set, a data set, and then I need a statistic, that means an X bar, for example, which is a statistic, or any other estimate that I am going to compute, and then the distribution. As I said earlier, you have the observation data in the mean estimation example, from which you compute X bar, and we also compute f of X bar. These are the three things that participate in inferential statistics, not the full statistical data analysis, but inferential statistics, or you can say hypothesis testing as well. So, what is a statistic? What is the formal definition of a statistic? The formal definition of a statistic is, as I had explained earlier, it is that it is some function, mathematical function of the data that you have obtained. The G is the one that we use to denote this function, and the output is theta hat. Strictly speaking, I should not have a theta hat there, I should have some other random variable, but we will assume that the statistics are being calculated for the purpose of estimation. Now, the reason I say this is, there is a subtle difference between what a statistic is and what an estimate is. A statistic is some general function of the observations that I am probably computing or calculating for the sheer joy of it, I do not know, right. There may not be a great purpose to computing the statistic, whereas with an estimate there is a definitive purpose, there is a goal in mind. I want to, I am estimating, I am subjecting the data through this function G so as to estimate some parameter. That is the prime difference between a statistic and an estimate, but we will not observe such differences in this course. We will use the term estimate and statistic interchangeably, because we are going to use the statistics only for hypothesis testing, not for the sheer fun of it, right. So, we will denote theta hat, the statistic by theta hat, and remember, and we have to keep telling this to ourselves, that theta hat is also a random variable in its own right, because it is being computed from a marriage of several random variables, a collection of several random variables. All the uncertainties actually will creep into theta hat as well. And remember that there is yet another requirement for the statistic, which is that it does not require the knowledge of the unknown parameters of f. For example, if I take sample mean, then to compute the sample mean, all I need is the data, I do not need to know anything more, alright. So, let us look at these two examples at the bottom. I have x bar, which is a sample mean, 1 over n sigma xi, that is a random variable. X bar is a random variable, it is a statistic, because on the right hand side I know everything, I do not need any knowledge, additional knowledge. Whereas in the second example, I have a new variable, random variable constructed from x bar, which we do routinely. In fact, we should get used to this in hypothesis testing of means, where I am constructing what is known as a standardized sample mean, x bar minus mu by sigma, let us say, okay. Now, this z is called a statistic if and only if I know mu and sigma. If I do not know what are this mu and sigma, this mu is the mean of the PDF which is generating the data for me, and sigma is, let us say, the standard deviation of the PDF, or sigma could be the standard deviation of x bar as well, which I do not know. We will show later on that the standard deviation of x bar can be calculated knowing the standard deviation of the PDF that is generating the data and the sample size. So, that sigma can be thought of as sigma x by root n. In any case, this z is called a statistic only when mu and sigma are known, whereas x bar is a statistic always, because the right hand side is not a function of any parameter of the PDF. That is the subtle point that also one has to remember in calling something as a statistic. And remember, I think you should now relate this word statistic to the steps that we have outlined in the general procedure in the motivation lecture. We said identify the parameter of interest, collect data, and then compute the statistic. What is the test statistic? The test statistic is nothing but the statistic that you are going to use for the test, which is being computed from the data. That is what is the test statistic. So, a few important points to note, again something that I have been repeatedly saying. Knowing G, typically we know the function or the formula, you can say loosely, that we are going to use to compute the statistic or the estimate. We can construct the PDF of theta. Now, this is not such an easy task in many situations. In some situations it is quite easy depending on the function G. For example, if G is linear, like in the sample mean case, it is easy to construct the PDF of theta hat. On the other hand, if G is non-linear, like we will see in the maybe in some other complicated estimation exercise, maybe not in this course, then it becomes difficult to derive the PDF of theta hat. Essentially, the nature of G determines how easy it is going to be for me to determine how the randomness in x will propagate to randomness in theta hat. If it is linear, it is fairly easy, I can use central limit theorem and so on. If it is non-linear, then very rarely, maybe in 1 or 2 circumstances I can actually find out, but by and large I have to resort to what are known as Monte Carlo simulations to figure out the PDF of theta hat, but I need that for hypothesis testing. I need f of theta hat. Fortunately, in this course we are going to work with statistics for which the PDF of theta hat is already known in theory. I do not have to really turn to simulations for any help. That is the good news. And also again the technical term, as I said earlier on the board, these distributions of statistics are known as sampling distributions, which are very useful in estimation and hypothesis testing. Now, we are going down further, we are slowly narrowing down to our problems of interest, which is that of hypothesis testing of mean, variance, proportion and correlation. Therefore, the statistics of interest for us are sample mean, sample variance, sample proportion and in bivariate analysis sample correlation. Now, having said this, I should also tell you that the hypothesis tests are for the mean, variance, proportion and correlation, one of these. It does not mean that I have to use only these statistics, I can use any other statistic that will help me test those hypotheses. As an example, suppose I want to test the hypothesis for the solid propellant burning rate case, which is the hypothesis test on the mean. I do not have to use sample mean as a statistic, I can use sample median also, right. I can use any other estimator of mean. The only reason why we choose sample mean is, of course, it is simple and a lot of times it is good and it has some nice properties, its PDF can be determined easily and so on. However, if you know that the data is prone to outliers, your data can be contaminated with a few outliers, then sample mean can actually end up being a wrong choice, maybe sample median is a better choice, because sample mean is not a robust statistic. If you look at the theory of statistics, there are different classes of estimators, robust estimators, unbiased estimators and so on. Robustness has got to do with how sensitive the statistic is to outliers in data, in which case maybe it is best to use sample median. But if you are sure there are no outliers, then it is better to work with sample mean, because it will give you the least error estimate, it is called so-called efficient estimate, alright. So, the bottom line to remember is that the hypothesis test is whatever it may be, mean, variance and so on. I can use any relevant statistic to test the hypothesis. The choice of the statistic depends on a few considerations: what kind of data, whether the data contains outliers or not, and equally importantly how easy it is for me to obtain the PDF of that statistic, alright. Now, before we really plunge into the sampling distributions of the sample mean and so on, let me take this opportunity to also tell you that statistics, as I said, the word statistic is more or less equivalent to estimate with some subtle differences that I had pointed out. And likewise, the inferential statistics is analogous to estimation, or is a part in fact of the estimation. Estimation theory is a very broad field that is applicable to all branches of engineering, medicine, social sciences and so on, and at the core of any statistical analysis is an estimation, as we have been discussing. So, it is important to be also familiar with term estimation, and we may be interested in estimation theory in estimating parameters of a distribution or model parameters or maybe signals, and in state space modeling maybe state estimation and so on. In this course we are only obviously going to be worried about estimation of parameters of distribution and estimation of model parameters in linear regression, because all our hypothesis tests are in those contexts only. So, estimation is a very broad theory, and again a point that I have been saying, it is very important to actually tell this to ourselves, that any estimate that I construct from data is going to be a random variable, and it is because it is a function of the sample size, right, and of course the randomness in the data. So, in this context there are several questions that one asks in estimation. For the common question that is asked is how good is the estimate, right. In the estimation of mean, if I use sample mean, I would like to know how good is the sample mean as an estimator. What do we mean by good? There are two things that quantify goodness, but both are talking about the closeness of the estimate to the truth. One measure is accuracy, which looks at the averages of the estimates. Now, here is where I just want to tell you as to why an estimate is a random variable, another way of looking at it. We have been saying because it is a function of the random sample, it is a random variable, that is all right. But if I want to understand truly what is this randomness business in an estimate, Let us go through this very simple thought process. I collect data, that means I have one data record, I perform one experiment where I have generated n observations and from where I construct one estimate. I construct another experiment, I repeat the experiment under the same conditions, I will get a new data record, the values of which will be different from the values that I got in the first experiment. Now from the second data record I construct another estimate, that is I have x bar from first experiment for example, x bar from second experiment, and likewise think of this as a thought process where I am conducting infinite experiments, number of experiments, I am repeating this again and again and again. Then for each data record I have an estimate. Everything held the same, I am getting different values of x bar, that is the mark of a random variable, right. We defined, remember we defined a random phenomenon as everything else I hold constant, but outcomes are going to be different. So, I have held everything, the experiment is same, everything, the sample size is same, I am collecting the same number of observations, same sensor, yet the outcome that is of interest, which is the estimate, is changing from experiment to experiment to experiment, and therefore it qualifies to be a random variable and therefore it has its own PDF. So, let me actually show you shortly an illustrative example highlighting all of this, but let us finish this first. So, for just now we said per experiment I have an estimate. Suppose I were to take the average of all such estimates from all those experiments, and if that average hits the true value, then we say it is an accurate or an unbiased estimate, right. On the other hand, I am worried about the variability of the estimate from experiment to experiment, which is characterized by the variance of theta hat, and the technical term for that is precision. We keep hearing these terms, high precision instruments and so on. There it is about instruments, sensing instruments that are repeatedly used to measure the same thing. I hold the process the same, I use the sensor repeatedly to see if it gives me the same reading. Take a thermometer in your home and keep measuring the body temperature at the same location around the same time, just repeatedly, and see if it gives you the same reading. But of course, there remember it has a resolution, that means it cannot show perhaps beyond the first decimal. So, you may think it is giving you the same reading, but if you are to actually go into the third, fourth decimal and so on, you will see even the second decimal it may give you a different reading. So, there is going to be variability in the readings there. Here we are talking of variability in the estimate, they are one and the same almost. So, we say here that the estimate is more and more precise as the variability in estimates across experiments decreases. As the variability becomes lower and lower, the estimate becomes more and more precise. Which is more important to us in estimation? Typically precision is a lot more important than accuracy, both are important. So, given a chance we would like to have an accurate and a precise estimator, but if we have to sacrifice one for the other, normally one sacrifices accuracy for precision, because of a simple reason. If I sacrifice precision for accuracy, then that means I am okay with having high variability of estimates. What does that mean? That means in one I am okay in obtaining an estimate of let us say 6.4 in for the sample mean in one from one experimental record, whereas another experimental record would have generated maybe 9.7. That is a very high variability. What does it mean? That means that the estimate that I am constructing from an experiment is not reliable. So, the precision is a measure of reliability. From one experiment alone, I may not be able to draw meaningful conclusions, or reliable, not meaningful, but reliable conclusions. There is going to be a large error in the estimate across experiments. I do not want that, and therefore, precision is a lot more important than accuracy, but nevertheless both are important given a chance. And then there are other kinds of questions. The most important question in estimation that is of interest to us is, what can I say confidently about the true process from the estimate? It is exactly what we have been saying right from the beginning of this lecture. And before we move on to sampling distributions, that is learning what is the distribution of sample mean, sample variance and so on, we may want to look at this general results that will help us in deriving the sampling distributions. So, before we move on to learning the sampling distributions, it is probably better to get a feel of what this sampling distribution business is all about. We have had a lot of discussion, theory and so on. So, it will be nice break to move into the practical illustration in the software that we are using, which is the R, and let me show you through an illustration what sampling distribution is all about. So, here I have the R studio in front of me, which basically is a GUI, and through this we are going to understand what is the concept of a sampling distribution and then get back to the theory. Let us say I am going to again go back to the same example of estimating the mean, and we want to try and understand what is a sampling distribution of a mean of sample mean. The mean of the population is a truth, that is a deterministic quantity, sample mean is a random variable. So, let us do it this way. Let us actually generate a random sample from a Gaussian distributed population. So, the problem setting is as follows. If I take R norm, which is the random number generator that gets me numbers randomly from a Gaussian distribution of mean 0 and standard deviation 1, that is what is the R norm routine in R. Likewise, you have many other in many other software packages you have similar random number generators, like for example in MATLAB you have rand_n. Now, R claims that the R norm will get you random numbers from a Gaussian distribution with mean 0 and variance 1. Suppose I want to actually test this claim made by this particular software. So, let me write that clearly on the board, outline this portion here. What R is actually claiming is that the true mean of the population, the Gaussian population generated from which R norm is sampling is 0. So, R says there is a population here with f of x is Gaussian for R norm with mean 0 and standard deviation 1. We will write this as variance being 1. This is what when I use R norm in R is going to sample numbers from this population. Now, suppose I want to test this claim that truly R norm is getting numbers from this population with mean 0. I will assume that this is okay, this is correct, sigma square is 1, I have no contention about that, but the only contention that I have is mu is 0. Now, I can formulate a simple hypothesis test, which is the hypothesis is that mean is 0, that is in the absence of any information the default claim made by R holds, because I am not doing anything. So, whatever claim they have, they have the right to take that claim. Once I decided to test their claim, then I formulate this alternate hypothesis, no, that is not true. Now, the only way I can test is to sample, because the actual possible numbers that you can get from this Gaussian population for all practical purposes is very, very large, you can think of it as infinite. So, what we will do is to test this claim, we are going to randomly sample 100 observations from this Gaussian population. So, we are going to choose 100 observations and see if I can claim this. Of course, that is the eventual goal that we want to get to, but the intermediate step is to obtain a sampling distribution. We will first illustrate what is meant by sampling distribution and then talk about how that is useful in hypothesis testing. If you understand this example in its full clarity, then you have more or less understood the crux of or the philosophy of hypothesis testing. Whether it is mu or some other parameter, the procedure is the same. So now let us sample 100, randomly sample 100 observations from this Gaussian distribution, and the syntax for that would be R norm of 100. Of course, you can specify to make sure that mean is 0 and variance is 1. In R we specify standard deviation. So, we say this, and now I have this vector of 100 observations in XVec. And obviously, if I want to verify if it is Gaussian and so on, typically I plot a histogram and so on. We are not interested in that at this moment. What we want to know is what if I compute the sample mean from these 100 observations, what is the sampling distribution. So, how do I compute sample mean? That is very simple. I use, so mean computes the sample mean for you, and we have stored that in x bar. Let us see what x bar is. Alright. So, it is this value. Obviously, we do not expect x bar to be 0 because we have only taken 100 observations. You may think maybe if I take 10,000 or 100,000 observations, I may get 0, maybe. Let us do that. So, let us take another set of data where I have 100,000 observations. Very good. So, I have done that. Now, let us compute the sample mean from this fresh data. So, what is x bar 2? It is very small, but it is not 0, and this is going to be the case. You may increase the number of observations by one more factor of 10, you will get a lower x bar, but it will never hit 0. However, what probably we can see is as I increase the number of observations in my data, in my sample, or what we say as I increase the sample size, the estimated mean, which is x bar, seems to be converging to the truth. And this is what the law of large numbers essentially tells you, that the averages will converge to the truth as you increase the sample size. We will not go in that direction. Right now what we want to know is what is meant by sampling distribution of this x bar, right. So, let us get back to the 100 observation case. What we will do is we have already x bar from one set of 100 observations. Let us generate another 100 observations. Now, we will do this and store this in xvec2 and ask what is the, let us x bar 2 what is the value. Alright. So, this is a different value, that is exactly what I said earlier. Now, this instance here, the first instance where we generated is my first experiment, like my first experiment where I have generated 100 observations, and this instance of generating another sample of the same size is like repeating the experiment, same sample size, and x bar and x bar 2 are the sample means obtained from these two respective experiments, and obviously they are different in values because now I have a different set of 100 values, and if I keep repeating this, I will get different sets of data and different sets of x bar. Now, that itself is an indication that it is a random variable. I am repeating the experiment, same sample size, I get different values. How do I now get the sampling distribution? That is distribution of x bar, let us say. One way is to repeatedly do this, maybe put this in a recursive operation like a for loop, and repeat this perhaps 10,000 times, and then collect all the sample means from those respective 10,000 replicates of experiments, and then plot a histogram, because histogram of anything of a collection of data, at least of a random sample, sorry, will give us a decent idea of the probability density function, in this case for a continuous valued random variable. So, we can actually write this recursive operation, put it in a for loop. In each iteration of the for loop, we generate data, compute x bar and store the x bar from each such operation. and then plot a histogram. This is the sequence of steps we can do, but that sounds a lot laborious. In R there is a nice way of doing this in a single shot. We will do all of that using this. So, we will say hist of replicate, right. What does this replicate do? It repeats the experiment. What do we want to be repeated? First we have to specify how many times we want to repeat it. Let us say I want to repeat the experiment 1000 times. More number of times I repeat, better will be my estimate of the distribution of x bar. So, what am I going to repeat? Repeat the calculation of x bar. How many observations I want? 100 observations is what I am looking at, correct. And of course, I can specify what is the mean and standard deviation to be clear that what I am doing is correct. And let us say I want the histogram to plot the probability plot, just for the sake of it, because then I can relate the probabilities very easily. Very nice. So, here I have this plot where what I have on the y axis is the density function. Straight away we see that this x bar has a Gaussian distribution, right. You can straight away say by looking at the histogram that it has a Gaussian distribution. If there are doubts on this, then either we can increase, pretty much we can increase the number of replicates or perhaps the number of observations. In fact, we will learn in the lecture that theoretically x bar follows a Gaussian distribution regardless of the sample size when the samples fall out of a Gaussian distribution. Here the samples are coming from a Gaussian distribution family. We have 100 not samples, observations, and 100 observations is what I have taken. So, I am linearly combining 100 such observations, and theory tells us that when I combine linearly n Gaussian distributed random variables regardless of what is n, the resulting variable is also going to follow a Gaussian distribution. That is a property of a Gaussian distributed random variable. So, x bar is actually following a Gaussian distribution. I can test this in many different ways also. For example, I may wonder whether this is true only for this case or is it true for several other cases. So, I leave it to you to play around with different means and different standard deviations and so on, but observe in each of that two things. One, that x bar follows a Gaussian distribution. Two, look at where the x bar is centered around, that is the PDF of x bar is centered around. On the y axis you have f of x, and on the x axis you have the count, that is the range of values of x bar. So, for example, many values of x bar in this interval are that is a lot of the probability of finding x bar. Let me put it this way, the probability of finding x bar in this range here within the vicinity of, let us say, minus 0.1 to 0.1 is quite high, whereas the probability of obtaining an x bar beyond minus 0.3 or plus or minus 0.3 is very low, right. And let me also show you something, that whether the samples the observations fall out of a Gaussian distribution or not, it still, the x bar will still follow a Gaussian distribution. All you have to do is go and change here the f of x, that is the population distribution, to let us say uniform distribution. So, the point I am trying to make here is whether the samples the observations fall out of a Gaussian distribution or they fall out of some non-Gaussian distribution such as a uniform one, x bar will still follow a Gaussian distribution. You can see things have not changed, right. Sorry, right. So, now there is something that you should notice as in between in this plot and the previous plot. So, let us go back to the previous plot. The PDF is is a Gaussian and is centered around what value? The origin. That means the mean of x bar is 0, which happens to be the mean of x also. So, x bar has its own mean, x has its own mean. Now, turn to the next case where we have generated data from a uniform distribution. Again, f of x bar is Gaussian and is centered around what? 0.5. When I changed from R norm to R unif, I said I specified this parameter 0 and 1. That means I am sampling from a uniform distribution within the interval 0 to 1. What is the average of a uniform distribution? Recall the examples that we went through. The average is a plus b by 2. That is, the mean is a plus b by 2. That means the true mean is 0.5. And you can see once again f of x bar is centered around 0.5, which is a true mean. So, in all of this what we are seeing is that the average of x bar seems to be the same as the x bar, the true mean of the population. As we said earlier, that means this is an unbiased estimator of the true mean. Now, coming back to the hypothesis testing, and we will close the discussion there. Let us go back to the Gaussian case. R claims that the R norm samples from a Gaussian distribution with mean 0 and 1, alright. Now, I have to test this hypothesis. What am I going to do? I am going to do the same thing, but not replicate here. I am only, in practice I will have only one data record. So, I will obtain only one x bar. Now, suppose from one data record, let us say I obtain x bar. So, x bar is collected from 100 observations. I will indicate this at the bottom here. It turns out that it is minus 0.15. Okay, this is what I get from 100 observations. All right. Now, from this obviously x bar is different from the truth, and we know it is going to be different from the truth. There are many ways now, using common sense I can understand what is hypothesis testing. One way of looking at it is, well, I was supposed to get 0, but I got minus 0.15. Should I consider this to be significantly different from the truth? Okay, that is one way of looking at it, whether the difference between the observed value and the truth is significant. That is one way of looking at it, but we will pose it in a different way to just shorten the discussion. We will assume that this to be the truth. We will say, let us say this is the truth. Let us say whatever R is claiming is correct, all right. Then we ask, if this is true, and if this is the case, that is I have n equals 100 and I am also given that this is correct. So, I know this is correct, this is what I have collected. So, there is no uncertainty about this, and this is what I am going to test. Now, I shall ask the question, if holding all of these things, is this a probable, how highly or lowly probable this value is? Of course, we can't ask exactly this, but what is the probability, for example, of the sample mean taking on values within the vicinity of this? In other words, we are asking, if all of this holds good, the null hypothesis holds good, the number of observations being fixed and the variance being known, is whatever I have observed a high probable value or a low probable value, less likely or more likely. So, as an example, suppose I say I worked very hard, a student null hypothesis, student worked very hard, all right, but it turns out that the on the exam the performance is very poor, all right. Then the teacher, let us say, would want to test the claim, student's claim. There is a probability that even if the student has worked hard, the student can end up with poor performance because the paper was actually very, very difficult and probably asked questions that never fell within the purview of the subject. There is a probability, but assume that is a very low probable case, then the poor performance is not so commensurate with the claim being made by the student that the student worked very hard, as a simple example. So, then what would you conclude? You say most likely it is probably that the student did not work very hard, something like that. So, likewise here, if this is true and if the x bar given all the rest of this to be true, if this turns out to be a low probable value, then most likely this null hypothesis is not correct. So, if you turn to the PDF, you can see that minus 0.15 is not a very unlikely value, but what is likely and what is unlikely is something that we have to decide upfront, which we call as a critical value and so on, and that depends on the error that I am willing to tolerate. Remember, there are going to be two different kinds of error. One, that this null hypothesis is true and I end up rejecting it. The other being this not being true and I still do not reject it, right. This not being true and then I still do not reject it. So, one is called a type 1 error, the other is called a type 2 error. Depending on the error that I incur, I will fix a critical value. So, if you look at the probability plot there, minus 0.5 is not such a improbable value, but on the other hand, in some other weird experiment for the same process, there may exist one realization. There may exist one realization. It is possible that you when the days are bad and so on, you may end up with some sample such that this turns out to be minus 2.305 or plus 2.305. So, you suppose this is the only realization that you have and it got you this x bar. This is no longer valid. This is a realization that you have such that your x bar works out to be 2.3. Obtaining such a realization takes a lot of bad luck, but let us say you really obtain that and then you obtain x bar this way. So, now you say this is the only realization that I have. X bar is a fairly reliable estimate, that is where the precision of the estimate is important. We say I can rely on the estimator is not that bad. Now I ask, given this to be the true, how probable is this value? I say the probability is extremely low, this is a very rare chance. So, it is more likely that this is wrong and you end up rejecting the null hypothesis, but all of that depends on what kind of realization you end up with. So, that is what is the crux of hypothesis testing, that you will normally hold the null hypothesis being true and then test, and that is why the null hypotheses are typically of equality types, right. If this was a null hypothesis, then it would have been very difficult to compute the probabilities of x bar or any estimate. That is point number 1. Point number 2, any hypothesis testing will have an error because we are looking at probabilities. And number 3, you should also see, and we will see that later, that this result of rejecting or not rejecting not only depends on the realization, but depends on these factors. If I change this 100 to let us say 5, then again things will change and so on. But we will see more of this in the next lecture, where in the next part of the lecture, where we will talk of sampling distributions of mean and then followed by sampling distributions of variance and so on. So, we will take a break at this point and then return to the theory in a short while. Thanks.